This morning we discussed how to solve absolute value equations, and we're going to move on to 13.4, module 13.4, which is solving absolute value inequalities. And we started off with this example in class today: absolute value of x equals 5. Figured out there are two possible solutions that would satisfy this, which is 5 and negative 5. Absolute value of 5 is 5, and absolute value of negative 5 is 5 as well. But let's go ahead and shift gears and change this to a greater than or equal to sign instead. And let's take a look at this. Okay, if we plug in 5, 5 is greater than or equal to 5, right? So that's going to make sense. If we plug in 6, absolute value of 6 is greater than or equal to 5. Absolute value of 7 is 7. That's bigger than 5. Absolute value of 8, also bigger than 5. So it looks like one of our solution sets is going to be x is greater than or equal to 5, right? Any number that's bigger than or the same as 5 is going to make this inequality true. But are those the only numbers that are going to make this inequality true? Well, let's think about it. What about if we were to plug in negative 5? Absolute value of negative 5 would be 5, which is equal to 5. What about if we were to plug in negative 7 or negative 8 or negative 9 or negative 10? Those negatives will all turn into positives, which would in fact be bigger than or equal to negative 5. So it's also true that x can be less than or equal to negative 5 as well. So these are your two possible solution sets. X is greater than or equal to 5, or, and I hope you remember that from a few months ago, but compound inequalities, x is less than or equal to negative 5, right? So the majority of the time when we are dealing with absolute value inequalities, we are going to end up with a compound inequality, either and or. And if you have greater than or equal to, it's most of the time going to be or. So if we were to graph this, if you remember how to graph compound inequalities, we have negative 5 here. We're going to have a solid dot, and we're going to be going to the left. And then we have 5 here. We have a solid dot. We're going to be going to the right. And that number line represents all the possible solutions for this compound inequality. So when we're solving absolute value inequalities, we'll follow these steps. You could write these steps down and read them yourself. The KISS method will keep one of the inequalities the same. Then for the other inequality, when we split it, we would switch the inequality symbol and switch the sign of the second number. And I'll show you what I mean by that in just a moment. Let's do number 3. We have absolute value of x minus 1 is greater than 6. So we're going to split this up, just like we did this morning with equations. And the first inequality is going to be exactly the same. X minus 1 is greater than 6. But the second inequality, we're going to keep it. We're going to keep the x minus 1 part, switch the inequality symbol, so flip it over to less than, and then switch the 6 to a negative 6. Okay? And we would solve both of these inequalities. So we add 1 on both sides, add 1 on both sides, and we would get x is greater than 7, or x is less than negative 5. And this would be an or compound inequality. In fact, you might want to write this down in your notes. Anytime your original inequality has a greater than or equal to sign, and the absolute value bars are isolated, then it's going to be an or compound inequality. Whereas anytime it's less than or equal to, and the absolute value bars are isolated, then it'll be an and compound inequality. All right. Now, this is just review from what we did back in Module 2 or whenever we did compound inequalities. So to graph this, x is greater than 7 or x is less than negative 5, we would have an open circle on negative 5, and we'd be going to the left. Okay, and then we would have an open circle on 7, and we would be going to the right. And that would represent our possible solutions. All right, let's take a look at number 6. So number 6, just like with equations, if there's stuff on the outside, you're going to want to remove everything on the outside first and then split it. So here we have the absolute value of x plus 3 minus 1 is less than 5. So if we get rid of this minus 1 first, we add 1 on both sides. That would give us the absolute value of x plus 3 is less than 6. And then we split it. First one's going to stay the same. Keep the first one the same, which is x plus 3 is less than 6. Then we keep the x plus 3 part the same. Then we switch less than to greater than, and we switch 6 to negative 6. Okay? And we'd solve both of these inequalities. So we'd subtract 3 on both sides. That would give us x is less than 3. And then we'd subtract 3 on both sides over here. And that would give us x is greater than negative 9. And remember, I told you that if you have less than or equal to, it's going to be an and compound inequality. And if and what I meant by that is if you have less than or equal to once the absolute value bars are isolated. Okay. Whereas if you have greater than or equal to once the absolute value bars are isolated, it's going to be an or. And if you remember from that module, and compound inequalities graph together, or compound inequalities graph apart. Okay, so this will be and. I forgot to do interval notation for that or compound inequality, but for and it would just be, oh, I'm sorry, it wouldn't be a bracket because we're not including it. It'll be a parenthesis. Negative 9, comma 3 would be the interval notation. And we're starting on negative 9. We're going to have an open circle on negative 9 because it is greater than. And we're ending at 3, right? So we're going to have an open circle on 3. That's just going to be anything in between that. Would be our solution to this absolute value inequality. That's all we're going to talk about today. We'll do some more of these, and we'll do some word problems as well tomorrow. Just make sure you have those steps written down before tomorrow's class. See you tomorrow.